Hi, everybody. Welcome.
Hi, good afternoon.
Good afternoon. Welcome, guys. Hi, everybody. My name is Olga. I'll be running this tonight's webinar. We have a set of webinars for you guys for the regions. Yesterday, we did geometry together. Today is chemistry. And Monday, we will finish off with algebra. So I want to give everybody a few minutes to get settled down. Everybody should be able to see my screen. You guys should be able to chat as well if you have any questions. I'm going to give everybody like 1 to 2 more minutes to get settled down and the last participants to sort of trickle in from the waiting room, and then we'll get started shortly. All right, guys, so it looks like most everybody is here. I'm going to take a second to introduce myself again. My name is Olga. I'm a longtime Kweller Prep tutor. I recently graduated medical school 2 days ago, and I'm really happy to be hosting these free webinars with you guys in the evenings. If you guys have any questions at all about a concept, a topic, a question, the medical path, high school, anything in between, I'm more than happy to stay later and answer them. And I'm excited to get started. So today is our chemistry day. We'll be reviewing a true Regents exam. So this is a real released old Regents exam that I pulled. And we'll just be going through the multiple choice questions for today. Into my sort of webinars, I try as much as possible to sort of overteach. So you guys will see me doing that a lot because I want to use the questions they're giving us in this particular Regents to show you guys the breadth and the depth of information. So I tend to overteach to give you guys more information, concepts that you can then apply to other questions, not just these questions. So I use these questions just as topics. We'll do hopefully we finish the entire multiple choice today. We'll do notes. I recommend that you guys take as many notes as possible as we are going through it together, just because it'll help you remember everything better. But I always share my email in the beginning and at the end of class, and anybody who attends my webinar, you can just shoot me an email and be like, hey, I was in your webinar, and I'll reply back with a PDF of the notes so you guys don't have to worry about missing anything, okay? All right, so I know your Regents exam is like in a few weeks, so we've got some time. So it's a great time for you guys all to be listening in and starting to prepare. So let's go ahead and get started. Okay, starting with number 1, we have which subatomic particles are correctly matched with their charges. So this is testing particles and charges. So first question for you guys is, which subatomic particles do we know? Yeah, right? The basics, right? So there are protons, there are neutrons, and there are electrons. And now the next part of this question is, what are their charges? So we have to know that protons are positively charged and electrons are negatively charged, making the correct answer choice 2. Protons are positive and electrons are negative. If we go through all the other options, they are obviously incorrect. We know that neutrons are neutral, so this is what makes choice 1 incorrect. Choice 3, protons are positive. And choice 4, protons are positive and electrons are negative. So all the other options we can completely eliminate. Good. Anybody have questions on the first one? First one was pretty straightforward. Okay, next, the gold foil experiment. So who remembers the gold foil experiment? So let's take a second to review our sort of atomic concepts and the idea of the atom. So there's different topics on the exam, right? The first one that we're going to go over is the atom, because that seems like that's what's coming up in the first few questions. So over time, our understanding of what an atom is has evolved. And there are certain experiments that are highlighted on the chemistry regions that they want you to know, and they are testable. So the first one that I want to talk about is Dalton's model. So Dalton's model was a really preliminary understanding of the atom. What Dalton told us was that elements are made up of atoms. And he learned that all atoms of one element are the same. So atoms of a singular element are the same. And then the next word from there, from element, we then get compound, which is multiple elements. So compounds are formed from combinations of atoms. So that was Dalton. That's the first beginning understanding of what an atom really is. The next one is Rutherford, and Rutherford is the one that did the gold foil experiment, which is what this question is testing. So Rutherford experiment, what he did was he took gold and he bombarded gold, he shot gold with a bunch of alpha particles. And does anybody remember what was the result of that experiment? What happened when he shot the gold with alpha particles? Yeah, correct. Most particles went straight through. Correct. And what that showed is that the atom is largely empty space. So that's the big takeaway for the Rutherford experiment or gold foil. The key word that you guys should memorize is that the atom is mostly empty space, and there's a small, densely positively charged nucleus, which is where all of our protons live. So let me take a second to write that down. So he bombarded gold foil with alpha particles. Who knows what an alpha particle is? Yeah, so alpha particles are 2 protons and 2 neutrons. They're positively charged. So what happened was he shot these alpha particles at gold, and what happened was most of them went through. So let me see if I could like draw it out for you guys in a reasonable way. So here's, let's say, my gold slate, and then here's the alpha particle. And what happened was when he shot these alpha particles, most of them just went straight through, right? So there's a bunch of arrows where they just went straight through in all different directions because the atom is mostly empty space. But there's this little piece in the atom that has, you know, all these positively charged, right? Here's my atom, that's huge, right? And then here are all the rings orbiting it, and then I have some electrons that live here and here. And you can see that because the electrons are like all around, it's really easy for the particles to just miss them, because most of that, you know, outside of the rings and where the electrons orbit in that one space is all empty, which is why those positively charged alpha particles, right, alpha, which is 4, 2, can go directly through. Does that make sense? But every once in a while, an alpha particle would hit this densely charged nucleus and it would bounce back. And he basically figured out that only happens in this small middle part of the atom. So what he discovered is that the atoms were mostly empty space, but there is this small, densely positively charged structure, right? And at that point, there was no name for it yet, but we now know that as the nucleus, and we now know that that is where protons live. So based on that, if we go back to this question, there's a clear answer here. Which is what? Right, exactly what we just talked about, choice 1, which is that atoms are mostly empty space. Does anybody have any questions on the Rutherford experiment? Now, this part, this next one about electrons being located in shells, this was a little bit later. This was more like the Bohr model or the most modern theory, which is the wave mechanical model. So let's finish our sort of atomic models, just so your page of notes is complete. But this second experiment, this Rutherford experiment, is what question number 2 was testing. The next one is the Bohr model. So the Bohr model, at this point, you know, all we knew was that the atom was empty space and there's this positive center. We didn't really know that outside of this empty space were orbitals with electrons that are moving. That was the next step that came along in the Bohr model. So the Bohr model added to that small positively charged nucleus, they added now that there are electrons in circular orbits. So the electron part came next. So the way that you guys should learn it is kind of a story. Dalton discovered the atom. Rutherford said that the atom is mostly empty space with a positive center. Bohr then said that the atom is mostly empty space, small positive center, surrounded by electrons in circular orbits. So that's kind of like the step-by-step of how we got to modern atomic theory. So the Bohr model is small, densely positive charged nucleus surrounded by electrons and then finally, after Bohr comes modern day atomic theory, also called the wave mechanical model. So what is modern day theory? Modern day theory just builds on this idea of electrons in a circular orbit. Instead of a circular orbit, we now understand more of like an orbital. And it's this idea, it's not like a perfect circle necessarily. And you guys will learn the specifics as you go into like higher and higher scientific classes. But the idea is that in the first electron space, it might be like a circle. But in the second electron space shell, it might be more like the electrons are somewhere in like Imagine that this is three-dimensional. So in the first plane, it's like flat, the electron is somewhere else. And in the second shell, perhaps the electron is either above or below. So it actually gets a little bit more complicated in three-dimensional versus just like a 2D image of like increasing circles and the electrons live somewhere in those circles. It's more like the electrons live in specific shaped clouds depending on which level. So that is modern day atomic theory. So what you guys have to know is kind of the story of it building. So finally, we get here where we believe that there is a small, densely positive charged nucleus surrounded by electrons moving in an electron cloud. And orbitals are areas where an electron with a certain amount of energy is most likely to be found. So in the newest sort of molecular theory, there's no like certainty. So we don't for a fact know that the electron lives exactly here the way that I drew it out. It's more like there's the space and most likely the electron lives somewhere there. So whenever you guys see the word orbital tells you that this is the most modern day theory. So orbital tells you that the answer should not be Bohr model or Rutherford experiment. It's very, very modern. It's wave mechanical theory. So that is a keyword for the most modern atomic theory. All right, so those are our four models. I'm going to number them for us. And it's most important that you guys know these. These will definitely come up on the Regents. And I recommend that you learn them sort of like additively, right? We start basic and then we keep adding. We start with Dalton, who said, here's an atom. Rutherford, who said, positive nucleus, mostly empty space. Bohr, who now said, positive nucleus, empty space, we've got electrons. And most recent, where not only do we have electrons, but they live in these sort of electron clouds, and we refer to the areas where they live as orbitals. So that's kind of the story of our atomic theories. Okay, so that took us through some of the atom questions, 1 and 2. Let's move on to number 3. So we have the bright line spectrum of an element is produced when excited state electrons blank. So how do we get an electron to go into the excited state? Yeah, right? For an electron to go into the excited state, we have to add energy. And then for an electron to then go back, that means what's happening? That means energy will be released, right? It's the opposite of adding energy. So now we have to think, are we putting it into the excited state when the light happens, or are we bringing it back when light happens? And the way that you can remember this is think of light as energy, right? So light is the energy that's being released when an electron moves back from its excited state back to the lower energy. So the answer here is choice 4, and the release of energy, that is the light. So that's always how I remembered it. Does that make sense? So they left no space for notes. So I'm going to keep making a new page. But this is a very, very important sort of concept. So when we think of electrons in an atom, the first point is that each electron in an atom has its own distinct amount of energy. When all the electrons are in the lowest possible energy, that's what we call our ground state. So whenever you guys see the word ground state, that means that everybody is basically home. Everybody is exactly where it should be. All the electrons are at their lowest energy forms. Now, what happens when an electron gains a specific amount of energy? So when an electron gains enough energy, a specific amount of energy, it's able to be pushed from its ground orbital, from its normal home, up to a higher orbital. And then instead of calling it the ground state, we are now in an excited state. So in an excited state, it just gained energy, right? It absorbed energy. And you can figure out that an electron or that an atom is in its excited state when the configuration doesn't match on the periodic table for that number of electrons. That's when you can figure out, oh, something's different, right? That one of the electrons moved. So when the electron moves up, it needs energy to go to that higher excited state, right? You need energy to be excited. So what happens when the electron returns from the higher energy state back to its normal lower energy state? It emits energy, usually in the form of light. And that's how we identify an element via the bright light spectrum. So that's what this question was testing. So number 3 is when an electron returns All right. So is everybody comfortable now? So to go from a regular to excited state, we absorb energy. And then to go back, we release energy in the form of light. So the bright light spectrum is formed. That bright light is the energy that's being released after we're moving from excited back to regular. That's why it's choice 4. Does that make sense to everybody? Okay, next one is pretty simple. Number 4, how are the elements on the periodic table arranged? Correct, right? So the elements in the periodic table are simply arranged by atomic number. Number 2, that's exactly how the periodic table is, arranged. The order of the periodic table is based upon the atomic number, which is going up from left to right. Okay, and then number 5 is asking us about electronegativity. So this is kind of getting to some trends, some periodic element trends. Let's see, did they give us a picture of the periodic table? Maybe in the end? I guess not. Okay, so who remembers their periodic table trends? What's the trend for electronegativity? Yeah, electronegativity increases as you go up this way. Good. Let me just post a picture of our periodic table for us. So we can write out the trends. Okay, so for electronegativity goes up this way. And horizontally, it goes up this way. So these are electronegativity trends. So electronegativity goes up from left to right, and it goes up the higher you are in the group. So when we look at group 15, right, which is this, the element that is the most electronegative there is nitrogen, like you guys were saying, which is why the answer is 3 nitrogen. Now, while we're doing this, what are the trends for ionization energy? So the trend for ionization energy is the same as electronegativity. Yep, absolutely. So not only electronegativity, but I'm also going to label this as ionization energy. Okay, what other trends do we need to know for this exam? How about atomic radius? Yeah, atomic radius has the opposite trend. So atomic radius is the opposite. So it increases as we go down a group, and it increases from right to left. So it goes this way. This is going to be atomic radius. These are sort of the main trends that you guys should know. These are like sort of the basics of the trends and the way that they go. I like teaching them in this order because it's easy to color code and remember. Electron negativity and ionization energy, E and I, go together, and then atomic radius is on the other side, and it kind of goes the opposite way. And then there's a trend for like metallics. It kind of goes diagonally. It's not a perfect trend, but just in general for you guys to know, once we move this way, the non-metallic character increases. And when we move this way, elements get more metallic. That one is extra, but those three are the basic trends that everybody should know. Everybody taking the Regents should 100% know. All right, we got through 1 to 5, and we did a big review of the atomic models, periodic trends. Any questions so far on anything that came up? Okay, so let's keep going. So the next one says, which term represents the simplest whole number ratios of the atoms of elements in a compound? So this is kind of a definition question. The key is the simplest whole number ratio. So by definition, simplest whole number ratio of atoms of elements in a compound, that is the empirical formula. So what that means is basically if you have, it's like a simplest whole number ratio. So let's say that you have, sulfur dioxide. Let's say you have disulfur dioxide, right? We have this compound. Di means two, right? So we would write that as S2O2. but the empirical formula is the simplest whole number ratio. So we have to use a little bit of math, right? And remember when back in the day when you learned about like simplifying fractions, that's kind of what empirical formula does. So it looks at these values and it says, oh, they're both divisible by 2. So the simplest whole number ratio, the empirical formula, would just be SO. You can kind of cancel these out or simplify them both dividing by 2. Does that make sense? So that is by definition what empirical formula mean, and that is what they mean by simplest whole number ratio, right? Ratio and simplest are the key words for an empirical formula. Does that make sense to everybody? So I can give you another example. Let's say we have glucose, right, which is C6H12O6. Let me just write it smaller. We've got C6H12O6, right, which is glucose. Then we've got C5H10O5, which is ribose. And then we've got C2H4O2, which is acetic acid. And then we've got CH2O, which is formaldehyde. So why am I telling you all this, right? These are 4 different molecular formulas. They're all different molecular formulas, right? But they all have the same empirical formula because when I simplify this, right, all of this can simplify to a 1 to 2 to 1 ratio. Does that make sense to everybody? 1 to 2 to 1 ratio, 1 to 2 to 1 ratio of carbon to hydrogen to oxygen. So although all of these have 5 different molecular formulas, they all have the same empirical formula. And what would the empirical formula be in this case? Yeah, good. It would be C1H2O1, but you don't have to write the ones. It's kind of like a coefficient. So it'd be CH2O. This would be our empirical formula here. Okay, moving on to number 7, we have how many electrons are shared in a triple bond between 2 atoms? So what's one bond? Each bond is 2 atoms. That's what you guys have to know. So this one is going to be 6. Absolutely. So every single bond is 2 atoms. So one bond is 2 atoms, a double bond is 4, and a triple bond is 6 electrons. So you would never get an odd number. So definitely we would be able to eliminate 3. And in this case, since it's a triple bond, it would be 6. Good. Okay, how about number 8? Yeah, correct, right? So how do we break a bond? Right? So first of all, we definitely know that a bond is breaking, right? Because we're going from 1 to 2. So we know that we took something and we broke it apart. So we definitely know that a bond is broken, right? So I can get rid of this and I can get rid of this. So I'm really picking between 1 and 3. Now we have to think, in order to break that bond, do I have to put energy in? And the answer is yes, right? Those things are bonded to each other. They're sharing their energy. They're happy. In order to break that connection, we have to put in energy. Like you think of like carotting, chopping them apart. That takes energy, that takes input. So you have to put in energy to break that bond, which is why the answer is 3. You have to absorb energy to break that bond. Now let's practice drawing out Cl2. What would that look like? What kind of bond are they connected by? So how do we do that, right? Just for practice, we look at our periodic table, we find chlorine, we're in group 17. What does that mean? How many electrons do I have? I've got 7 electrons, right? Good. So now there's 2 of them, right? So I've got 1 chlorine with 7 electrons, got another chlorine with 7 electrons. So now together, right, I've got 14 electrons. So I have Cl, Cl, 2, 4, 6, 8, 10, 12, and 14, right? They're sharing. And the reason why this bond is good, let's just think about it for a second, is an atom is most happy when it has 8 electrons, right? So usually chlorine has 7. So usually chlorine alone has 7, right? Not as happy as when it has 8. So in this state, this chlorine is super happy because it has 8, and this chlorine is happy because it also has 8. So they're happy to share because that puts them in that perfect 8. So that's another way for you guys to realize that in order to break that bond, you're making both the chlorines unhappy, right? Because they want to have their perfect 8. So that's another reason why you have to add in energy, why energy must be absorbed in order for that bond to be broken, because we're making those atoms less happy when we're breaking that bond, because they don't get their perfect, valence shell of 8. Does that make sense to everyone? So the next question, is addressing some of the concepts that I just started talking about. So the next question says krypton atoms in the ground state tend not to bond with other atoms because they're blank. So krypton, where's krypton, right? Here's our periodic table. Krypton is one of the noble gases. It's in group 8. So what's special about these noble gases? Yeah, they have a full valence shell, right? It's exactly what I was talking about before. Their outermost shell already has 8, so they're happy. That's why they're not trying to bond with other ones, because they are already good, right? They're fulfilled. They have all their electrons. They don't need to bond with anybody. So let's think about what is wrong with all the other options, right? So innermost shell contains 2 electrons. Nobody cares about that, right? We care about the last shell having 8. Third electron shells contains 18. Again, 18 is not what we care about. We want it to be 8. And then it's 18 electrons in general, I think, for krypton. And then a second electron shell contains 8. Again, not important to us because we want the last one to contain 8. All right, and the last question on this page, number 10, asking us how we can classify all matter. So matter is a little bit of a complicated word sometimes for students. How would you guys define matter? So let's give ourselves a definition for matter. So matter is classified as either a pure substance, which can either be an element or compound. What a pure substance means is that it has a constant composition, constant properties. So what that means is like, imagine I take gold, right? I take gold from my necklace. I take gold from Queen Cleopatra's jewels, hundreds of thousands of years ago, or I take gold from somebody in a new civilization 10,000 years down the line on Mars. If I test this gold, it will always have the same properties, right? The same metallic compounds, the same sort of number of protons, electrons. Gold is gold. Does that make sense? It's an element. Same idea with carbon, right? If I take carbon from our atmosphere today, and I take carbon from when the dinosaurs lived, which is what they do with carbon dating, it's still carbon, right? The properties of carbon are the same. So that's what we mean by pure substance. A difference of that is a mixture. A mixture is not always a pure substance, right? So if I take sand from Mexico and then I take sand from Mars, and then we start looking at the composition of that sand, it won't always be exactly the same sand, right? So some sand might have more carbon, some sand might have more nitrogen, some sand might have more seashells, some sand might have more salt. It depends where we get the sand, right? But that's very different than something like a pure substance, like gold or any one of the elements or a compound, right? Like salt, NaCl is salt anywhere. It doesn't matter where we get it from. It's always NaCl and it has the same compounds. So that's what's important to understand about matter. Matter is a pure substance or a mixture of pure substances. Does that make sense? So let's write out that definition. Okay, versus a mixture, the proportions of components in a mixture vary, like I was telling you guys before. So now that we understand what matter is, we can go back to this question and then we have an answer, right? Matter is either a pure substance or it's a mixture. And the key word here is all matter, right? Because an element is matter, a compound is matter, a mixture, an element is matter, but we want to classify all matter. So the most encompassing answer is choice 4. All right, done with the first 10 questions. Anyone have any questions, any concepts that brought anything up that you guys want us to review? Nope. Okay, let's keep going. So the next one, we have which sample at standard temperature and pressure has the same chemical properties as 10 grams of aluminum? So what determines chemical properties? We kind of just talked about it in our discussion of matter. What determines chemical properties? What two things are they giving us in this question? They're giving us an element and they're giving us amount. Does the amount of something determine its chemical properties? No, exactly. So that's kind of like the trick part here. The only thing that determines the chemical properties is what that thing is, what that substance is. So the same element will always have the same chemical properties. So this is almost a trick question. The answer is just 5 grams of aluminum, because aluminum is aluminum. Whether we've got 5 grams, 10 grams, 15 grams, or a million grams, that aluminum will have the same properties. So the same element will always have the same chemical properties. Next, we have which sample of matter cannot be broken down by a chemical change? Yeah, correct. So the answer is 1. By definition, an element cannot be broken down. That is one of the definitions of an element. All of the other ones are not elements, right? They're made up of separate elements, so we can break them down, but an element is the most broken down aspect. Like we can no longer break it down. And antimony or antimony is an element. So the definition of an element is that it cannot be broken down by chemical change. Okay, next we have number 13. We have based on table F, which 10-gram sample, when thoroughly mixed with 1 liter of water at room temperature, forms a heterogeneous mixture. Okay, let's see if we have table F. I don't think I have table F in my copy, so we'll just skip that question. All right, let's move on to number 14. So we have a 1 molar NaCl solution at 1 atmosphere and a 2 molar NaCl solution. So what's the difference between 1 molar and 2 molar? What is molarity? What does molarity describe? Yeah, molarity is a measure of concentration. Good. So it's not a trick question. Which one is more concentrated, 1 molar or 2 molar? So the 2 molar solution is obviously more concentrated. So basically what we have is salt and water. And in one solution, we have, let's say, 1 tablespoon of salt and water. And in the second solution, we have twice as much, 2 tablespoons of salt and water. So what happens when we have a more concentrated solution? What happens to our boiling point and freezing point? And you guys can think about like your real life. Like, why do they say to put salt in pasta when you're cooking pasta? Or why do we throw salt when it snows and when it's icy? Why do the trucks come around it and put salt on the streets? It's actually the opposite, right? So let me tell you guys logically, right? So we add salt into our water, not to make it boil faster, but to make it boil at a hotter temperature. So when we put in the pasta, it'll cook faster because it's cooking at a higher temperature. Does that make sense? So salt increases our boiling point and it actually decreases our freezing point. So the reason we throw salt onto the streets is so that it has to get even colder for the streets, for the ice to freeze. Does that make sense? So we're trying to lower the freezing point when we're throwing the salt on the street because it won't get cold enough for it to freeze. Does that make sense? So it's kind of a little bit of backwards thinking, but you guys have to know that salt and concentration increases boiling point and decreases freezing point. So it's kind of the opposite of what you may expect a little bit. And the way that I always thought about it is it's getting colder and it's getting hotter. So you remember which direction the increase is, and then the opposite one decreases. But both of them are moving towards their extremes, right? Because things boil when they're hot, so it's getting even hotter, the boiling point goes up. Things freeze when they're cold, so it's getting even colder, the freezing point goes down. So that's how you memorize which direction it goes in. So in this case, it would be higher boiling point and it would be lower freezing point 3. And it checks out with logic of why we put salt on our streets when it's icy and salt in our water when we're making pasta. Okay, The next one is asking us what is three forms of energy. So temperature is not a form of energy, so any choice with that we can just get rid of. And alkalinity is a property, how alkaline something is, it's also not a form of energy. But all three of these are forms of energy: electromagnetic, nuclear, and chemical energy. Okay, moving on to number 16. They're asking us about ideal gas. So when you think about ideal gas, you think about your own life. You should think about what's your ideal vacation, right? Where do you want to be? So I want to be on a beach and I want to not have any stress, right? So you should think low pressure and high temperature. So that's always how I remembered what an ideal gas likes, because it's exactly what me and you would like. You want low pressure, low stress, and you want high temperature. So choice 2. Okay, next one we have, which sample of argon gas has the same number of atoms as 100 milliliter sample of helium gas at 1 atm and 300 Kelvin? So what is this testing? Something that we haven't talked about yet. So who remembers Avogadro's hypothesis? What did Avogadro say? Let's see if I can squeeze it in up here. So what Avogadro's hypothesis stated was that for gases, there's a predictable relationship of volume, temperature, pressure, and the number of molecules. So if you have two gases and they have the same pressure, temperature, and volume, then they must contain the same number of molecules. So whenever that is asking about number of atoms or number of molecules, that's a key word for you guys to realize that they're asking you about Avogadro's hypothesis. So again, I'm just going to write it down. So if two gas samples have the same pressure, temperature, and volume, then they must have the same number of molecules or atoms, right? Whatever you want to call them. So that is Avogadro's hypothesis. And that is what this question is asking us. So all I have to do is I have to match the amount, 100 milliliters, have to match the pressure, 1 atm, and I have to match the temperature, 300 Kelvin. So the only one that does that is going to be choice 4, right? 100 milliliters, 1 atm, and it's the same temperature. Choice 4. Okay. Next one is asking us about a chemical change. So what is a chemical change? Which one of these is a chemical change? So a physical change is when we just rearrange things that exist. Nothing new happens, we're just rearranging. So for example, if we take water and we boil it and it turns into a gas, I'm just rearranging the water particles into water vapor. It's still water, it's just a different phase of it. Whenever we're creating something new, that is a chemical change. So like you guys are putting in the chat, the correct answer is synthesis of MgO. That is a chemical change. All the rest of these are just phase changes. And chemical versus physical is really important. So I'm going to take a minute to write that down in our notes. So we have physical versus chemical changes. So physical change results in rearrangement of existing particles in a substance. The key is that no new particles result from a physical change. A chemical change does result in the formation of different particles with different properties. So you distinguish between chemical and physical changes based on whether or not new substances form or not. So obviously in this question, where are we? Here, the new substance was MgO, right? And the key is synthesis. So this tells us that it's new, right? New substance. Okay, moving on to number 19, we have which property is determined by the structure, arrangement, and interactions of the molecules of a substance at a given temperature and pressure. So structure, arrangement, and interaction. So basically what this is telling us is physical state, right? This is distinguishing between solid, liquid, and gas. All that has to do is the structure and the interactions of the molecules. The rest of these do not change based on those things. Next, we have a collision between reaction particles is most likely to result in a reaction when the particles have proper orientation and proper length. So what are the two things we need? We need proper orientation and we need energy, right? We need energy to start a reaction, correct? And finally, the last one on this page, we have given the equation representing a system at equilibrium, which statement describes this reaction at equilibrium? So what does equilibrium mean? Yeah, equilibrium means balance, right? It means that as means that on both sides, we've got concentration that is the same. We've got the same amount of 2NO2 and we've got the same amount of N2O4 and it's perfectly fluid. And the rate of it being transformed this way is equal to the rate of it going backwards, right? That's what this double arrow mean. So the rate of this is equal to the rate of this. So it's constantly, as one NO2 becomes N2O4, one N2O4 becomes NO2. It goes perfectly in equilibrium. Does that make sense? Which is why the concentration on the two sides must be constant, not necessarily equal, right? We can have more or one of the other, but constant is our key word for whenever we're dealing with equilibrium. The rate of the reaction, of the forward reaction, and the rate of the reverse reaction is constant, as well as the concentration on both sides is constant. So the key word whenever you guys see equilibrium is that word constant. Does that make sense? So be very, very careful with a choice like one. That is like the fake answer here. It's the answer that they want you to fall for. It is not the correct answer, right? The concentrations do not have to be equal, but they have to be constant because the rate of that forward reaction equals the rate of the reverse. So as soon as the concentration of N2O4 goes up because one NO2 became N2O4, the concentration of NO2 also goes up. So they stay constant. Does that make sense? All right, guys, so we're about halfway through our lesson, our webinar, and the multiple choice. So I want to give you guys all a 5-minute break, the same way I did yesterday. So you guys can all stretch, come back rejuvenated, grab some water, bathroom break, whatever it is that you guys need. And then we'll continue at 6:05, 6:06, okay? And we'll keep going the same way. We're almost done with the first part of the multiple choice. All right, guys, one more minute of break, but sort of start coming back. All right, guys, final stretch. We're almost done. Let's keep going. Okay, so we're up to number 22. So we have, which phrase describes the effect of adding a catalyst to a chemical reaction in order to increase the reaction rate? So what does a catalyst do? Yeah, catalyst speeds up reactions. Good. So by definition, a catalyst, the point of a catalyst is to speed up a reaction. So now the question is, well, how does it do that? So the way that it does that is it provides a separate reaction pathway with a lower activation energy. So some of the particles can now go a different route that has a lower activation energy, and some of them still go the original route. So the answer choice is choice 1. It provides a different reaction pathway with a lower activation energy. So the key is that lower activation energy, right? It makes it easier to hop over that hill. Definitely not higher activation energy, right? So these are the choices that you could eliminate. Higher activation energy will not make the reaction go faster because you have to use even more energy, even more time to climb up that hill. So we can eliminate 2 and 3 and 4. Okay, systems in nature tend to undergo changes which way? Basically, this is asking us about entropy, right? What is the natural way a reaction goes? Yeah, so entropy is all about disorder, right? So we're going to go low energy, greater disorder. So that's choice 2. Always. That's the natural way. Okay, next one, number 24 is asking us which element must be present in an organic compound. So this is a definition question. By definition, in an organic compound, we must have carbon. Next one, number 25, is asking us about a saturated hydrocarbon. So what that means is we want a hydrocarbon that has all of its hydrogens all in a single bond. So the general formula for this that you guys should memorize is it's CnH2n+2. So for example, if we're checking C2H2, right? So then it should be C2H2 times 2 plus 2. So C2H6, which is not an option. So we know it's not C2. So then let's check C6. So C6, C2 times 6 plus 2. So it would be C6, H14. Excuse me, it should be an H. So the correct answer here is choice 4. And then we can prove it to ourselves, right, by drawing. So imagine we've got 6 carbons, right? 1, 2, 3, 4, 5, 6. Happy carbon has 8 electrons around it, right? So that means 4 bonds. So that means all of these need to be hydrogens. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, right? So that checks out. So this is our formula. But even if you guys don't have that memorized or you don't know, where to look for that formula, you don't need it because you can prove to yourself that this is fully saturated. The rest of them would not be fully contained with hydrogens. And we can just practice and draw out C2 fully saturated. So again, all your carbons need to be connected to a hydrogen. sharing 8 electrons. So this would be 1, 2, 3, 4, 5, 6. It would be C2H6, just like we proved below with the formula. Good. Okay, moving on to number 26, we have which reaction occurs at the anode of an electrochemical cell? So did anybody learn the mnemonic for this? Yeah, so I always learned an-ox. So at the anode happens oxidation, or oxidation happens at the anode, an-ox. Anode is oxidation. And then for a cathode and reduction, I usually think of red cat. And then that's how I remember an ox and red cat. An ox is anode for oxidation and red cat is reduction at the cathode. Moving on to number 27, we have which statement describes the 2 types of reactions that occur in operating electrochemical cells? So these are again definition questions. So we have to know that voltaic cells, voltaic is a battery. So spontaneous reactions happen in voltaic cells versus non-spontaneous reactions occur in electrolytic. So it's backwards. It's not 1. The correct answer is choice 3. Electrolytic needs a battery, so that's what makes it non-spontaneous. It needs energy. Okay, now that we're getting to acid-base theory. So what is an acid according to acid-base theory? Does it accept hydrogen atoms or does it donate hydrogen atoms? Yeah, correct. So according to acid-base theory, an acid is an H plus donor. That would then make a base an H plus acceptor. So basically what this is, another way of saying this is the Bronsted acid-base theory. Just in case they throw that word at you guys, so you know. Bronsted says that acid is H plus donor, like we just said, and then a base is then an H plus acceptor. Okay, next we have which emission will be released from an unstable iron 53 nucleus? So for this question, we have to use some of the tables that they provide that I don't have open here. But when you look at the tables, you would then see that a positron is being emitted, and that's how you get to this answer. But you need the use of the tables. So we'll skip this one. And then finally, the last one, what is a potential risk with radioactive isotopes? And again, we can use logical reasoning for this one, right? What do we know about radiation and radioactive isotopes, natural disaster like Chernobyl? Obviously, the biological exposure is very, very damaging. So this one is pretty easy. The answer is just 1. Okay, so moving on to part B. we have which electron configuration represents the electrons of a phosphorus atom in an excited state. So to do this, we have to go back to our periodic table. We have to find phosphorus, and we see that the ground state for P on phosphorus, we see that it's in the third period, and we see that it has 15 electrons. Right? So here's phosphorus. It has 15 electrons. It's in the third period. So what does that tell me? We've got phosphorus and it has 3 electron shells, right? That's what the third period tells us. How many electrons go in the first shell? 2. The way that you guys can always remember that is on the periodic table. It just goes 1 and 2, right? For the first period. So in our first shell, we just got 2 electrons. So we have 1 and we've got 2, let's say. Now, after that, all of them want to fill up by 8s. So in the second shell, it won't be happy until we've got 8, right? So 1, 2, 3, 4, 5, 6, 7, 8. So far we've accounted for 10. We've got 15 total. So the last 5 exist in the outermost shell. So its electron configuration in the ground state is going to be 2, 8, 5. Now, by definition, what does the excited state mean? What's going to happen in the excited state? This is our ground state. So in the excited state, one of the electrons jumps from its regular home into a higher orbital, right? So it can't be in the third one, right? We've got nowhere to jump. So it's going to be the second one jumping to the third one. So one of these electrons is going to get enough energy and it's going to jump to its place in a third shell. So it's going to go 2, 7, 6, which is then going to be, sorry, 2, 8, 6, which is then going to be excited state. Sorry, 2, 7, 6, correct. Because one of them is going to jump. Right, so when it jumps in the second one, we now only have 7 left. Does this make sense to everybody? This is pretty important. So what just happened? So 2, 8, 5 is our ground state. The question is asking us for excited state. So 1 is going to jump to a higher shell. So it's going to jump from here. So that's only going to leave 7 in the second shell and 6 in the third shell. That's what makes it excited. But notice that our total number of electrons does not change. We're still dealing with, phosphorus. So that's why this is 3. This here is ground state of phosphorus. Next, we've got 26.7 gram sample of which element has a volume of 3 cubic centimeters at room temperature. So what did they tell us? They gave us the volume and they gave us the mass, right? So you guys should always think about your units. What is the relationship when we take, mass divided by volume? What is that ratio called? Yeah, that's density, right? So what we would do here is we would figure out the density. So density is mass over volume. So density is going to be 26.7 over grams over 3 centimeters cubed, which is going to divide into 8.90. And then the Regents gives you a list of tables, a table that has all the densities. So then you would go to that table and you would look for which element has a density of 8.90, and you would match it to the correct answer, which is nickel. Next one, which element is a non-metal and solid at standard temperature and pressure? So the non-metal part makes it easy for us to eliminate some things. So we should know that lead and sodium are metals. So we should be able to eliminate those easily. And then you know that nitrogen is a gas at STP, so that's out. And then the correct answer is sulfur. Next, they ask us for the molecular formula. So all we have to do is just consolidate and count. So we've got 1, 2, 3, 4 carbons, right? So at that point, we can already get rid of 1 and 2. We know that can't be our answer. Next, we count our hydrogens. We've got 3, 5, 8 hydrogens, so that doesn't help us. And then lastly, we've got 2 oxygens. So the correct answer is 4. So just for extra practice, I want you guys to give me the empirical formulas of all of these. So put in the empirical formula of 1, 2, 3, and 4 in the chat, and then we will review that. Okay, good, right? So most of you guys are getting the empirical formula. So as we reviewed before, to get the empirical formula, what we have to do is we have to divide all the values by their greatest common greatest common factor, GCF, right? So these, we can't do anything because we have this O here and it's not divisible by anything. So 1 stays C2H4O. Can't do anything there. The second choice, we can simplify all of these because all of these are divisible by 2. So this simplifies down to CH2O. Third one, again, we can't do anything because there's no value here for the O. And the last one, again, they're all divisible by 2. So this simplifies to C2H4O. Good job, guys. Now we keep going for 35. We have a substance conducts electricity in the liquid phase, but not in the solid phase. How do we classify that substance? So by definition, that is what we call an ionic compound. That's a property of an ionic compound, something that conducts electricity in the liquid phase, but not in the solid phase. So that's where we get choice 2. Okay, next one, we've got a student measured the melting point of a sample of gallium to be 309. Then we look on table S to get the real amount, the real melting point, which is 303. And how do we calculate the percent error? So percent error is measured minus accepted over accepted. So this we have to memorize. Measured minus accepted over accepted multiplied by 100%. This is percent error. So what's measured based on the student's experiment is 309. What's accepted based on table S, where you guys would look on the real exam, is 303. And then we divide by 303, multiply by 100%. So that is how we get the correct answer, which is choice 1. Okay, the next one is asking us which chemical bond is most polar. How do we figure out what is most polar? So what you guys have to know is that the largest difference in electronegativity results in the most polar bond. So what we would do is that there's a table that gives you the electronegativities. So what we would do is we would find the electronegativity of oxygen, of hydrogen, of selenium, of sulfur, and of titanium here, and then we would compare all of them. So in table J is where they give you all the electronegativity. So I'm just going to write them out for you guys here, and then you can practice doing this. So the electronegativity of hydrogen is 2.2. Electronegativity of oxygen is 3.4. For sulfur, it's 2.6. Selenium is 2.6, and Te is 2.1. So now that I gave you that information, I want you guys to do the exercise of subtracting and see which gives you the greatest difference, and that is the one that is the most polar bond. So just based on these numbers, right, we can kind of do the subtraction in our head. The greatest difference is going to be between 3 and 2 because the rest of them are all in the realm of 2. So the OH bond is going to have the greatest difference in electronegativity, which is what makes that bond the most polar. Okay, the next one is asking, what is the amount of heat required to melt 43 grams of solid magnesium oxide at its melting point? And they give us the heat of fusion. So what is our formula for this? Which equation would we be using? So heat of fusion, right? If you look on your reference charts, you're going to find that Q is equal to mass times heat of fusion. And Q is the amount of heat, right? That's what they're asking us, amount of heat or energy. So that is our answer in joules. And heat of fusion, you'll see the units are joules per gram. And then mass is in grams. So what you'll see is that the grams will cancel and you're always going to end up with your joules. So whenever I'm lost about the kind of formula that I need to use, I usually just look at my units and it kind of helps me figure out which numbers go where and which formula I need to use. So this proves to me that I have to multiply the mass by the heat of fusion. So now that I gave you guys that, all we have to do is plug in those two values, both of which are given to us. So they tell us that the mass is 43 grams, and the heat of fusion is also given to us as 1.9 times 10 to the 3. So all you guys have to do is put this into your calculator or multiply it, by hand. And you're left with the answer, which is going to be 8.2 times 10 to the 4th power. Okay, last one on this page. We've got this laboratory apparatus, and what they're asking us is, what is this being used for? So what they're doing here is they are distilling the water, right? They have a hot plate, they have salt water. When they are heating that salt water, the water is going to evaporate, right? It's in this condenser. The water vapor is now going to go here, and then it's going to come out, and as it recondenses, it's going to come back to water. Does that make sense? And once all this water evaporates, what's going to be left here is just salt. So this is the process of distillation of water. Does that make sense to everybody? They're just heating salt water, and then we end up with water in the receiving flask after it's vapor, and then it's recondensed, and then we're left with salt in the original flask. All right, guys, we're done with the next page. Let's take a minute to pause for questions. Any questions on any of the concepts we covered here? Then we'll move right along to the next one, number 40. We have solid aluminum has a specific heat capacity of 0.90 joules per gram times Kelvin. The question is, how many joules of heat are absorbed to raise the temperature of 24 grams from 300 to 350? So this is a similar question to what we practiced with, right? We're still dealing with heat capacity and heat and joules. So we're going to have Q, and we still have mass, but the difference is that we also have a change in temperature. So it's Q equals MC delta T, right? Or Q equals MCAT. So Q is what we're solving for. The mass is given to us, right, as 24 grams. So we plug that in. The specific heat capacity, that's C, is also given to me, 0.90 joules per gram times degree Kelvin. And then delta T is the change of temperature, so 350 minus 300 Kelvin. And usually what I always do is I check my units to make sure that I didn't plug in incorrectly, right? So the grams cancel and the kelvins cancel, and I'm only left with joules, which is what my answer choices are in, which is what heat is. So now the last part of this is that I just have to multiply this out. So this ends up being 24 times 0.9 times 50 to give us our final answer of 1100 joules. I'm going to skip 41 again just because I don't have table G. So let's move to 42. Which change favors the forward reaction? So who can tell me which concept this question is testing? So not just the answer, tell me what the principle is. So what I want to hear is that this is testing Le Chatelier's principle, right? So let's review Le Chatelier's principle. So what does Le Chatelier say? So Le Chatelier's principle predicts, he says that a system at equilibrium, whenever we disturb that system, we're going to shift the equilibrium in the direction that counteracts the change. So let's imagine that we've got this system in equilibrium. We're gonna have A plus B is in equilibrium with C plus D, right? Here's my basic equation. And let's create a table of stress, shift, and Y. And I want to go through, let me think. Let's go through 7 different stresses. Okay, so the first stress that I want to think about is concentration. So let's say I increase the concentration of A. So which way am I going to shift if I increase the concentration of A? Am I going to go forward or am I going to go back if I increase the concentration of A? Yeah, so you always are going to shift away from the increase. So if I increase the concentration of A, I'm going to shift away from the substance. So in this case, the shift is forward, and it's always away from increased substance. And now the question is why? What is the logic of that? Because now we have extra A, I need to use it up, right? How do I use it up? I combine it to B, I go forward. So the extra concentration needs to be used up. So now what's going to happen if the opposite happens? Let's say I decrease the concentration of a substance. Say I decrease the concentration of substance A. Which way am I going to shift then? If I decrease the concentration of substance A, it's going to be backwards, left, correct, towards the reactions. So it's going to be backwards or left. In general, you're going to go towards the substance. And again, the reasoning for that is we need to produce more of it to make up for what was removed. If I decrease the concentration of A, I need to make more of it to replace. Okay, so we just played the concentration game. Now let's play the pressure game. What happens if I increase the pressure of the system? I'm just going to put a 2 here to make it more interesting. What happens if I increase the pressure versus if I decrease the pressure? And next we'll talk about temperature. What happens if I increase the temperature? What happens if I decrease the temperature? Correct. Pressure only matters for gases, but let's say these are all gases. What happens? So when the pressure goes up, the side of the reaction with the fewer gas molecules is favored. So in this case, let's say we've got 3 gas molecules here, and we've got 2 gas molecules here, the reaction would go forward. Correct. So increases of pressure favors the fewer gas molecule side, decreases of pressure favor more molecules side. And what happens with temperature? So if we increase temperature, the exothermic reaction is favored. We go away from the heat or energy. And if we decrease the temperature, then we're going to go towards the heat or energy. And what happens if I add a catalyst? Is that going to shift the reaction anyway? So we talked about how a catalyst works, right? A catalyst just lowers the activation energy. It doesn't actually shift the rate of the reaction at all. So this is sort of a trick question. So a catalyst is not really part of Le Chatelier's. It's not going to lead to any shift. So that's why I wanted to include it here as separate from all this stuff. So now that we go back here, which change favors the forward reaction? So if I increase the concentration of O2, is that going to, which way am I going to shift? Right? So if I increase, we just talked about this. If I increase this, I'm going to go this way. I'm going to go forward. So the answer here is pretty straightforward. It's just choice 1. When I increase the temperature, right? Temperature is energy. It's on this side. So when I increase energy, I'm going to shift backwards. When we decrease the pressure, on this side, we've got 3 molecules, and on this side, we've got 2 molecules. So again, when I increase the pressure, I would go forward. I would go towards the less molecule side, but decreasing the pressure is going to make me go this way. And decreasing the concentration of SO2 is also going to make me go this way. So all the other choices by Le Chatelier are shifting towards the backwards reaction, but only choice 1 is going to shift us towards the forward reaction. Does anybody have questions on Le Chatelier? Okay, let's think about next one. This one's asking us about entropy. So we talked about entropy a little bit before. Entropy means randomness. So when we go from, solid to liquid to gas, entropy is going to keep increasing as we move from solid to liquid to gas, because in solid, everything is very rigid, right? We have a solid lattice arrangement. The particles can't move around a lot because they are stuck together in this form of ice. As things become liquid, right, they can shape different forms. So the particles have more random arrangement. And then finally, when they are gas, they can even take up more space. They have more ability to be even more random. So as we move from solid, liquid to gas, the entropy increases because randomness increases. Particle arrangement becomes more and more random, which is what is increasing its entropy, which is why it is choice 3. Okay, the next one, we've got propanal and propanone. They have different chemical properties due to what? So what are these endings telling us? Al andone. So these endings are part of organic chemistry. They're giving us different functional groups, right? So the al functional group is an aldehyde. So it's the prop part tells me how many carbons, and then the al part tells me how many, what the functional group is. And then what about propanone? What functional group is that? So one is for ketone and al is for aldehyde. So al is aldehyde and one is for ketone. And the only difference is that they have a different functional group. So ketone functional group, just for us to review, is going to look like this. This is propanone. This is propanone. And the functional group is this ketone, which I'm highlighting. And that is different than propanal because that functional group is going to be an aldehyde. So we're going to have so you can see that they are both prop because they each have 3 carbons, but the functional groups are different. This is our aldehyde functional group versus that is our ketone functional group. Good. Any questions on that? All right. The next question is asking us to name this compound. So what's our goal in naming? Do we want to have big numbers or small numbers? What's our goal? Like, what does IUPAC teach us? Yeah, we want to keep the smallest possible numbers, correct? So that changes how we count, right? So the first thing that I would do is I would find the longest carbon chain. Longest, find the longest uninterrupted carbon chain. So now we count. We have 1, 2, 3, 4, 5. Is that the longest or can we go better? 1, 2, 3, 4, 5, 6. Is that the longest or can we go better? 1, 2, 3, 4, 5, 6 in this direction as well. So it seems like 6 is the longest, right? So I'm looking for a hexane, right? Not 8. I can't get to 8 uninterrupted. So I get rid of 1 and 3. So I'm picking between 2 and 4. So now depending where you start numbering, right? If I start numbering from here, I can get 4 methyl, 5 methyl octane. Or what I can do alternatively is I can number from here and I can get 1, 2 methyl, 3 methyl. So because I want the lowest possible numbers, I'm obviously going to number from right to left. And my answer becomes 2, 3. Dimethyl, don't forget that because there are 2 methyl groups here. And then hexane, because it's our longest carbon, uninterrupted carbon chain is 6. Okay. Next, oh, perfect. We just reviewed some of the functional groups. So what is this functional group? What do we have here? So the functional groups are actually given to you in table R, so you don't have to memorize them. But the key is we have both an oxygen and a nitrogen. We've got a double bonded oxygen and a nitrogen. That is by definition an amide. Next one is asking us which substance is an electrolyte. Correct. So asking about electrolyte is basically like asking for an acid. By definition, electrolytes are substances that form ions in solutions. So let's take a minute to define electrolyte. So an electrolyte is a substance which, when dissolved in water, forms a solution capable of conducting electrical current. So when this dissolves in water, right, we're gonna have H plus and Cl minus, which is what makes it an electrolyte. These substances are sugars, which will not dissolve, they will not break up into ions in water. Okay, next, number 48, we have an indicator is added to an aqueous solution with a pH value of 5.6. Which indicator is paired with its observed color in this solution? So for this one, you would also use table M, and you would find which indicator is which color at which pH using table M. And then you would just see that at this pH of 5.6, methyl orange is the indicator that is the correct color. You'd have to use table M for this one. All right, we've got the last two multiple choice as we're finishing up our chemistry webinar. So we have solution A has a pH value of 2, solution B has a pH value of 4. How many times greater is the hydronium ion concentration in A than in B? So let's talk about pH values for a second. And that should help you guys answer this question. So for every change in pH of 1, the acidity changes by a factor of 10. So what does that mean? Let's do an example. So a pH 4 solution is 10 times more acidic than a pH 5 solution. Correct. So now in this case, we're going from 4 to 6, right? Oh, from 2 to 4, sorry. So this is a difference of 2 units. Each unit is 10, right? So it's going to be 10 by 10 or 100 times. So the pH 2 is 100 times more acidic. Good. What pH is a neutral pH? So neutral is pH 7. Good. All right, and our last question, we have which net change occurs in both nuclear fission and nuclear fusion reactions? So nuclear fusion and nuclear fission, the basics of either of those reactions, nuclear energy comes from mass converting to energy. In both cases. So that's why the answer is choice 1. But let's review. What is the difference between fission versus fusion? That's kind of what it sounds like. Fusion, when things are fusing, yeah, they're combining. So fission splits one into, so fission takes at one heavy atom and splits it into two lighter atoms. So splits one heavy atom into two lighter atoms. Versus fusion, like the word sounds, fuse, combine, combines two lighter atoms into heavier atoms. But in both cases, they are converting mass to energy. That is the basics of nuclear energy. And that's the similarity between both of them. That's why it's not 3 and 4, because that's the difference between fission and fusion. All right, guys, so that sort of marks the end of our chemistry Regents free review. During this review, we went through all 50 multiple choice questions in this Regents exam, and I also tried to give you a conceptual review of many of the concepts that keep coming up, such as the atomic models. We did some acid-base stuff, periodic trends, Le Chatelier. All of these are common concepts that you guys will definitely see on your real Regents. I'm happy to stay if you guys have any questions about the Regents or anything at all that was mentioned in the webinar. I'm happy to stay later and answer. Anybody that needs notes, you guys can feel free to email me here and I will reply back with the notes. Somebody said, are there any more of these sessions? I taught a free geometry review yesterday, and we're gonna have free algebra on Monday. If you would like more of these reviews, I would recommend reaching out to Francis Kweller, who's the one that's organizing all of these. And I'm also available for private tutoring if anybody needs. So I put my email and Ms. Queller's email. There are none scheduled more for chemistry right now, but if you guys ask for them, if there's demand, we can definitely do more. Thank you guys. Have a good night and have a good weekend. Best of luck on your studies. Please reach out to me if you have any questions. Thank you. And if you need the notes, I sent my email. I'll put it in the chat one more time. I'll happily reply back with the notes. Thank you guys. Thank you so much. Have a good night. I hope it was helpful. Bye, guys.